Oh, it's, yeah. Okay, so hopefully all of you have dug into this and worked hard on it so far. There's one important thing I want to point out about this, is that the parameter that you're using for this parametric function is theta, right? So the t is now theta, but this is not polar coordinates. Those are two different things. Okay, so you're using that. So again, close enough. Okay, so in order to write her position, we call that point P, in terms of x and y, the parameter that you're using is theta. So you're writing, and that's this right here. So that's similar to the common trig angle and the polar angle, but this is not polar coordinates. You're just using theta as the parameter in this case. Okay? Polar coordinates are where the coordinates are r and theta. This is still x and y, so we're still dealing with rectangular coordinates. We're just defining each x and y as special functions of theta for this unwrapping scenario. Okay, so now that we're talking about polar coordinates and your project is using theta as the parameter, you got to separate that in your mind, okay? That this is still parametric function using the parameter t is now this angle. But this is not polar coordinates. Okay, doesn't make sense. You're writing x as some function of theta and y as some other function of theta. In polar coordinates, we know that. So let's review. So any questions about the project? And remember, so if you're going for extra credit, you're not only answering all the questions accurately, but you're showing some extra effort. You're showing understanding, proving things, whatever things apply that you think is going kind of above and beyond the questions asked. Okay? Like for instance, you may figure out how to get the area, but can you show an analysis of why that worked? Why does that work? So getting into the kind of the fine points of how an area in parametric gives you the area that you want. And we talked about that in lecture. Because why? Because we have curves up on top of themselves and they're going forward and backward, but we're still kind of using the same construct of y and x integrals to get area. So how are we getting the area that we want? Still thinking about areas from left to right of a positive function give us a positive area to the x-axis. Okay, so again, now these parametric functions, they're crossing over the same x value more than once, and they're going left and they're going right. How is it that it makes sense that we're going to get the right area that we want? So if you want to show some more detail in that, that's the kind of things that we want if you're going for extra credit. Okay? Any questions on the project due Monday? Okay. What the heck happened to my polar grapher? I don't like it. What happened? Try this. Okay, we're back. So we did this question. Let's do this question now. So find this point. 2 comma negative 2 pi over 3. So identify that point. And let's find the x and y coordinates of that point. and then write it 3 other ways in polar coordinates. So find 3 other ways in polar coordinates to write, to express that point in the plane. Okay, so here's the thing about polar coordinates. Positive r can point in any direction. Positive r doesn't mean to the right or up. Positive r always points in the direction of the terminal side of the angle. So wherever that angle is pointing, that angle can point in any direction, and then once that angle is set, positive r points in the direction of where the terminal side of the angle points. So the original, and so even though the points are expressed as r theta, but you really think it's really theta first. It's really theta first, and then once you get the direction set, then r is out from in that direction. So so think of negative 2 pi over 3 first, and that's the rotating to this into the 4th quadrant. Negative 2 pi over 3, and now that's the direction of positive r. So we go 2 units out. So was there a question back there? You're good? Okay. So yeah, we're going to sweep negative 2 pi over 3. That sets the direction of positive r, and then we go positive 2. All right, other ways to express this point. So there's an infinite number of ways now in polar coordinates that we could express that point, but only one way in x and y. There's only one x and one y that'll get you there, but there's an infinite number of r theta pairs that could get you there. So what was another one? Let's list some. Negative 2 and pi over 3. Does it work? So let's see. So I'm going to start with the angle from 0, and I'm going to do pi over 3. Maybe. Something like that. It's not landing right on it. But there's one in between. All right, that's good enough. All right, so there's pi over 3. What? That points up in the 1st quadrant. So the negative 2 would be in the opposite direction of positive r. So that would take you back down into the 4th quadrant. So that 3rd quadrant. So that's right. Another possibility. This works. Negative 2 pi over 3. What's another possibility? Just shout it out. 2 and 4 pi over 3. So we do the angle 4 pi over 3 first. Starting here, so we're going to go around to 4 pi over 3. That actually worked. And then we're going to go positive 2. So the direction of 4 pi over 3 is the same as the direction of negative 2 pi over 3. It's pointing the exact same place. So then we'd also have positive 2 with 4 pi over 3 would take us to that point. Who's got another one? 2 and negative 8 pi over 3. Let's try it out. So what is 8 pi over 3? That's 6 pi over, that's 2 pi. Basically, that's negative 2 pi and another negative 2 pi over 3. Is that right? So 8 pi over 3 is this. So what? So we go around the circle once clockwise, and then we go another 2 pi over 3. Again, that takes us on that same line down, pointing down in the 3rd quadrant. We go positive 2. So that works. Okay? So similarly, we could do 100 pi plus 4 pi over 3. What is that? 304 pi over 3. 2. Is that right?
Radius first.
Right. So let's see. I'm thinking angle first because that's the way you should think about it. So I wrote it wrong. So 304 pi over 3 means go around the circle 50 times. 2 pi 50 times, and then go another 4 pi over 3, and then go 2. So you get the idea that there's an infinite number of ways to express any point in polar coordinates. Questions on this activity? Is this making sense? I think the most confusing thing for students is they want r to point somewhere like always positive, like positive x or positive y. Positive r can point in any direction around the circle according to what the angle specifies. So angle first, and then positive r goes out from there. So you see, this has nothing to do with the Clara project. We're not expressing points with angle and then distance away from the pole, distance away from the origin, along that angle. That has nothing to do with the Clara project. Clara project is a parametric function. Okay, so let's take, I showed you a actual parametric function. So a parametric function is where we write r as a function of theta. So given different values of theta, it gives different values of r, and then if you continually plot all those points, you get a curve or a line or something in the polar plane. So let's start with an example of r equals, a nice easy one, r equals 2 sine theta. And here's how we're going to do these. We have to remember how to graph these functions, so like y equals 2 sine x, first of all, in rectangular coordinates, and then we're going to use the graph of y equals 2 sine x to get the covariation. We're going to use that graph as the covariation of r and theta to figure out how it's going to look in the polar plane. So can you sketch, if this is x and this is y, can you sketch 2 sine x? That's sine 2x. 2 sine x. 2 sine x. Okay? Not sine 2x. Can you sketch that? 2 sine x just in x and y coordinates, not polar, just in x, like a sine wave, right? A sine wave. Can you sketch 2 sine x? We all should be able to. We're going to have to sketch harder ones than that. So lots of us may have to review how to sketch these graphs. So sketch 2 sine x in x and y coordinates. So what's the period of that? How far does it go before it starts over? You should be thinking 2 pi. And then we're going to break that up into 4 pieces. Right? All these sine curves are based on kind of 4 pieces. All right, and then does 2 sine x, does that start at the, or so let's talk about the max and the min. What's the max and min of that sine wave? Yeah, it's going to get as low as -2 and as high as 2. So this is an easy example of things you're going to have to do. So we're going to have more complicated sine things, and you're going to have to brush up and learn how to sketch these. Okay, so we got 2 to -2. And so we got the min and the midline and the max. Does sine start its cycle at 0? Does it start at the min, the midline, or the max? Starts with the midline. Sine of 0 is 0. And then does it go down to the min or up to the max first? Right, so at pi over 2, the y coordinate is it's at its maximum. So it's going to be like this, then back down to the midline, then 3 pi over 2 is at the min, and then 2 pi is that's the best sine curve I've drawn all day. I wasn't drawing sine curves this morning. That's the first sine curve I've drawn all day. Okay, so here we go. So now what are we going to do? So now what is x? X is like theta. X is like theta, and y is our r. So now we're thinking of x in polar coordinates. This is our theta, and y is r. And so we're going to use the graph to help us sketch this thing. So we have x and y, or r and theta. We see how they covary together in this graph. And we're going to sketch it in the polar plane. So let's set that up to do that. But we're not ready to yet. Okay, so here we go. So what happens, we're looking at that graph, what happens as theta varies from 0 to pi over 2? Let's see if 48 will work. Perfect. Okay, so what happens as theta varies? So here's theta varying from 0 to pi over 2. Watch, ready? Here's theta varying from 0 to pi over 2. What does r do as theta varies from 0 to pi over 2? What does r do? What does the value of r do as theta varies from 0 to pi over 2? So you look at the graph. R starts at 0 and does what as theta varies from 0 to pi over 2? Increases up to 2. Increases up to 2. So what will that look like in the polar plane, thinking about how things are graphed? So it's going to start here at 0. So when theta equals 0, we get r equals 0, so we're at the pole. It's right there at the pole. So then we can think about theta increasing little by little. So now here's theta increased a little bit, and what happens to r? It goes up. So we get another point now, something like that. Increase r a little bit, or sorry, increase theta a little bit. What happens to r? It increases, so we're farther out now. See what I'm doing? So for increasing theta, that one between, yeah. So for increasing theta, oh, there it is. We're back. So what happens for each increasing theta? R is increasing, so we keep getting farther and farther out on that terminal ray. So here now, theta is even greater, so r is further out. And where am I heading to? So by the time theta gets to pi over 2, what should r be at? 2. So a little further again. And then almost there, so it's going to be almost to 2. Until at pi over 2, r is 2. So watch it again. As theta increases, every time theta increases, we get a point further away from the pole. So further away out on that terminal ray. So do you see that is accurate, or it's somewhat accurate for r increasing from 0 to 2 as theta increases from 0 to pi over 2. You see that? So every time theta increases, we're a little bit further out. Okay, and then what happens as theta changes from pi over 2 to pi? What happens to r? Goes back to 0. And can you see that it will go back to 0? It'll get, so as theta continues to increase, then our r value will get closer and closer again back to the pole, and in a symmetric way. Do you see that? So in a symmetric way, it'll head back to 0, from 2 to 0. So we can assume that's kind of the same points that we had before. I'll just sketch a couple of them. So now by the time I'm here, so what, maybe here it's something like that. So each time theta increases, r decreases, and then I'll just do it on the lines here. So then maybe like this, and maybe like this, and like this. So we get some kind of loop. We get some kind of loop. R goes out to 2. As theta increases from 0 to pi over 2, r increases out to 2, and then decreases back to 0 as theta goes from pi over 2 to pi. It looks like some kind of loop. Yeah?
How did you know how far along the lines?
I'm just estimating. So I'm not finding exact values of r. I was just eyeballing it. Does that make sense? So these are not precise points. I was just kind of eyeballing, going a little bit further out for each increase of theta. Is that okay? Yeah, we're just sketching right now. Other questions? All right, so then what happens from pi to 2 pi? So as theta goes from pi to negative 3 pi over 2, what does r do? Goes from what to what? This is the question we're going to be asking when we do this. As theta increases from something to something, r will change how? From what to what? So here it changes from what to what? 0 to negative 2. Okay, so here we are at pi. What will it be? What will it be like if r increases or decreases from 0 down to negative 2? What will we get? What quadrant will we be sketching in? But r is going from 0 to negative 2. So I'm going to be sketching in which quadrant? No, r is going from 0 to negative 2. This will be back in quadrant 1 again. So it will start at the pole. And then as theta increases to 3 pi over 2, r will be at negative 2. Where's that? Where's 3 pi over 2, negative 2? So this, okay, this is hard. This is students to sketch, especially when these functions get harder. So I hope you're really digging in and paying attention. I get feeling like some aren't. Okay?
So basically, this is just one circle.
What's that? So where is 3 pi over 2, negative 2? Where's 3 pi over 2, negative 2 at?
Same as pi over 2.
Right, the same as pi over 2 too. And so if r goes from 0 to negative 2, now it's going from, like, basically going from 0 to 2 on the red line. Do you see that? It's going to do the same thing. It's going to repeat. As theta goes from pi to 3 pi over 2, it's going to repeat what we did from 0 to pi over 2 because r is negative. And now that would put us back in the first quadrant. And then what about from 3 pi over 2 to 2 pi? What quadrant will we be in? Second. Increasing from negative 2, which is at the top, back down to 0, which would be sketching over there in quadrant 2 according to the red line. And it'll repeat what we had before. So basically, we get a loop from 0 to pi, and then we get the same loop from pi to 2 pi, sketching r as negative in the negative direction. So it repeats itself. So we get the whole curve in this, the period for the polar curve is pi. We get the whole curve, and we go from 0 to pi, and then we repeat it again every time we increase by pi. Okay, so what exactly is the loop? Is it an ellipse? Is it a circle? Is it something else? So here's how we can figure that out. So look at this. R is 2 sine theta. So can we rewrite this equation in terms of x and y? Can we rewrite this equation in terms of x and y? Well, we have sine theta. Does that relate to either of the coordinates? We found out last time. X is what and y is what in polar coordinates? R cosine theta and r sine theta. So we have sine theta. Is that equal to y? No, r sine theta is equal to y. So it would be really nice if this was r sine theta, and then it would just be y. But I can't just make this r sine theta unless I do what? Multiply both sides by r. So I could say r squared equals r sine theta, and this would represent the same curve. So now r sine theta is y. And what is r squared? So thinking about our x, if we have a point here that's r theta or xy, what is r squared equal to? So r is the distance from the pole. That's like the length along a hypotenuse. X and y would be like the legs of that triangle. So r squared would equal? Do you see that r squared is x squared plus y squared? So look, r sine theta is the same. Now I've eliminated r and theta, and I have it in terms of x and y. X squared plus y squared equals y is this same curve. It's this same curve as r sine theta. What is that?
Did you mean to drop the 2?
No. No, I didn't. Okay, it shouldn't take the TA to catch me on errors like that. Okay, we had 2 sine theta, so this is going to be 2 r sine theta. I need to make extra credit for students catching my mistakes. I wonder how much the attention level would go up. If I make a mistake or you're thinking something's wrong, please speak up. Don't let me dig myself a hole, okay? All right, so we said r was 2 sine theta. So the r squared then is 2r sine theta. And so r sine theta is y, so 2y equals x squared plus y squared. So what is this? It's what? Is it a circle? So we're used to circles in a different form. So can we get this in the form of a circle? That would mean getting subtracting 2y on both sides. And we're used to something with x squared and something with y squared. So what do we need to do? We need to complete the square here. We need to complete the square. What completes the square of y squared minus 2y? Remember, half the coefficient squared. Half the coefficient squared. So half of minus 2 squared is 1. But if I add 1 on this side, I got to add 1 on the other side. One step away. So I got x squared plus what squared? Now since we completed the square, we have a perfect square here. Y what? Minus 1 squared. So what is that? Circle, radius 1, centered at 0, 1. So it turns out what r equals 2 sine theta sketches in the polar that this is indeed a circle. So let's watch it. Ready? So I've got the function 2 sine theta here. And I'm going to let the polar graph do it. And we'll do it in blue. I'll do it in blue. Ready? So as r goes from, or sorry, as theta goes from 0 to pi over 2, r goes from, so that this is just showing the points. I need to show the curve. Here we go. I need this one. There we go. As theta goes from 0 to pi over 2, see r increases up to 2. Let's see that again. As theta increases from 0 to pi over 2, r increases from 0 to 2, and that forms a circular, semicircular arc. Then as theta goes from pi over 2 to pi, r goes back down from 2 to 0. And then if we go from pi to 3 pi over 2, see the blue point there, tracing on the red line, meaning negative values of r. 0 to negative 2, and then negative 2 back to 0 as theta goes from 3 pi over 2 to 2. So it traces it again. And we showed it algebraically that's the circle, center 0, 1, radius 1. Because r equals 2 sine theta, we did the math, is equivalent to this equation of x and y, which is the circle that we just drew. Okay, anybody have a question?
So if you add to the argument, does it just make that circle go around the origin?
Add to the argument.
Like make it sine of theta plus n, and then. Anyway,
So we're going to change these. We're going to do different ones. So yeah. So why don't you, let's try, let's see how this goes. R equals cosine theta plus 1. So what are you going to do? You're going to sketch that. So then you're going to change that to y equals cosine x plus 1 and sketch that. No calculators. All calculators are away. Y equals cosine x plus 1. You're going to sketch that in rectangular coordinates, like a sine wave. Then you're going to use that sine wave to try to ask, as theta increases through intervals of angles, what does r do? And you're going to use that to try to sketch the graph. Okay? So these are the easy ones. These are going to get a lot harder. Okay? These are the easy ones. Yeah.
If you add pi over 2 to the argument, does it just make that circle go pi over 2 over?
No, I think it'll just it draws the same circle but starting at a different place, right? Doesn't it just shift that theta?
Yeah, but so then this r would correspond to theta starting at pi over 2 or something, is what I would think.
Oh, so it would like draw this one over here?
Yeah.
Oh, interesting.
And then add different values into theta.
Yeah, because it's going to shift the curve, what, this way?
So now to rotate it.
Yeah, so you're going to get, so what do you want to do? N
F of n plus.
of 2?
Sure.
Yeah, right.
Okay, and it goes actually the opposite way. I would have thought. Oh, well, the shift is usually the
Right,
opposite
it's going to
side.
start saying, yeah. Sorry, I couldn't think on my feet fast enough there. That's 0, 1. 0. Theta equals 0, your part equals 1, right? Or equals 2, actually.
Yes.
Did you do it right? Okay, this was this one. Okay. So the first thing you're doing is sketching the plane and sketching the curve. You're not changing this into x and y. You're sketching the curve, y equals cosine x plus 1, and using it to sketch the polar curve. That's what we're doing. Sketch the curve, y equals cosine x plus 1 in rectangular coordinates, the wave, and then use it to sketch the polar curve. But don't try to change it into x and y. That's how you're going to sketch the, don't just guess what the polar graph is. So lots of you are going to need to review. This is cosine x plus 1. So quick here. As x varies from, as theta varies from 0 to pi over 2, what does r do? From what to what? So we're using that graph now to help us sketch the polar graph. We're not going to look at the last circle and guess what this one is. We're going to use this graph of y equals cosine x plus 1 to sketch the polar graph. As theta increases from 0 to pi over 2, r does what, according to that graph? Goes from 2 to 1. Do you see it? It goes from 2 to 1. So what does that mean? At theta equals 0, we're at 2. And by the time we get to pi over 2, we'll be at 1. Now that's not going to go like this. So let's look at the angles. So imagine it decreasing down to 1. Imagine it decreasing down to 1. Let's just turn the points on. So imagine it, I got the wrong graph. What's going on? Switched it. I didn't switch it. There we go. Okay, watch. So as theta goes from 0 to pi over 2, r decreases from 2 to 1. See how it does that? It's moving towards the pole as theta increases. So it did something like this. So as theta increases, r decreases to 1. Did something like that. Did you see it? Okay, now from pi over 2 to pi, from pi over 2 to pi, what does r do? Goes from what to what? It decreases from 1 to 0. So what does that mean? It keeps getting closer until when we're at pi, we're at the pole. Back at the pole again. So then for each successive angle of theta, increasing angle of theta, we're going to move closer and closer and closer to the pole. So it's going to do something like that. Watch it. So as theta increases from pi over 2 to pi, r decreases to 0. Do you see the actual point on the black line? The terminal ray. Okay? Then what happens from pi to 3 pi over 2? What does r do? Looking at our graph. From 0 back to 1. So that's kind of symmetric to what it just did, but now it's going back to 1. Watch it. Ready? In the third quadrant now. It's going to increase back out to 1. See it? R is going to increase back out to 1. Something like this. And then it's going to go from, in the last quadrant, from 3 pi over 2 to 2 pi, R goes from what to what? 1 to 2. Back from 1 to 2. It's going to increase from 1 to 2. So it's going to, watch it, see it? It's increasing back out to 2. As theta increases from 3 pi over 2 to 2 pi, it increases back out. Is it a circle? It's not a circle. This is not a circle. So if you guess, based on the last one, you guessed wrong. This is called a cardioid. Cardioid because it looks like a heart, kind of. Let's watch it sweep out here. Here it comes. Ready? Back to 0. So it's 0 at pi, and then increases to 1 in the third quadrant, and then increases to 2. That's called a cardioid. All right, so the next web work will be due Wednesday. So you